What forces besides the friction act on block A? Yeah.
The rope pulling to the left.
Right, so there's a tension. Tension can only pull, so there's a tension to the left on block A.
The weight of the 50 pounds.
Block A's weight, 50 pounds. I don't know the dimensions of the block or if it's homogeneous. I'm just drawing it. It looks like it's in the center. It's going to turn out not to matter because I won't have enough information to take moments in this picture. So the weight of the block of 50 pounds acts. Right, normal force. So between the surface of block A and block B, that surface prevents block A from falling through to the ground. So some normal force, I call it NA, acting on the block. And there'll be the friction force. We'll come back to that in a second here because we know it's parallel to the surfaces. It's not necessarily apparent which direction it should point. It will be, though, after the next step. So I'll just put a reminder up here. Don't forget about the friction force. That's FR. And we'll return to free body diagram 1. Let's move on to 2 and then come back. What forces are acting on block B?
25
Its own weight of 25 pounds.
The above weight of 50 pounds.
Not necessarily. NA, right. The normal force is shared. It will turn out through the equations to be 50 pounds, but we don't want to presume that. So equal and opposite normal force. The applied force P pulling to the right. The normal force between surface of block B and block C pushing up, so some NB. Again, if we were considering tipping, I would be putting in this unknown distance here. I don't have enough information in this problem, so I'm just drawing them somewhere on that line. Again, without taking a moment, it's not going to matter in this case.
Two frictional forces.
Right, this is where we will have a better idea of which way they should be pointing. If we're pulling the block B to the right, then we would expect that, since it's moving to the right, that both of those frictional forces have to counter that or be in the opposite direction. So now we know there should be a friction force A to the left and what I'll call friction force B to the left. Now it's easier to come back up here. We know that the friction force in this picture is to the left. So on the equal and opposite, on the other side of the surface, it has to be to the right. It might not be as apparent at this step that that friction force would be pointing to the right, or it might be, but in more complicated cases, there's sometimes one free body diagram, especially where we're applying a moment or applying a force, where then we definitely know which direction the friction should point. And sometimes we really don't know. If you go through the equations, we might come out with a negative friction force, and then have to go back and say, okay, our guess was wrong. Let's redraw it, recalculate, and make sure all of our normals and all of our frictions are positive. In this case, though, we should be relatively certain that this is the case. If FRB is to the left in this picture, then FRB is to the right in picture 3, and NB is up in 2, so down in 3. So finally, block C, what are the remaining forces that act on block C?
Normal force of C.
Right, the ground, preventing it from falling through the earth.
Weight of C.
Its own weight of 15 pounds. Right, in the scenario we described earlier, we predicted either block B will move to the right, independent of A and C, or B and C will be stuck together and move to the right, in which case we would expect then for block C to want to move to the right, so FRC should point to the left. And we took care of this friction, so that's done. These are the 3 free body diagrams. We don't know the length dimensions, so we will only be able to get 2 equations out of each one, though. On this one, yep. That should be A. Right, now any questions on the 3 free body diagrams we need? At this point, we still haven't put any of the motion considerations in. It helped influence the drawing of the friction arrows, but this is just general equilibrium. We're going to be able to get 2 equilibrium equations out of each of these drawings that still don't take into account the motion scenarios that we're going to come up with. Sum of forces in each of our pictures, no sum of moments. We get 6 equations. I rearranged them so that they're a little bit easier to use. It does turn out that that normal force A is 50 pounds, normal force B is 75, normal force C is 90, 90 being the sum of the three weights. But in the free body diagram, we don't want to assume that. We use the equations to prove that. So the only thing linking together picture A and B is normal force A. I don't want to automatically say that that's going to be 50 pounds. Because if we have an inclined surface, or if there were another force in the vertical direction here, this would not be the weight of the block above it. It does turn out that way, though. So equation 2, 4, and 6 give us those. And I rewrote the friction forces in terms of the applied force and in terms of the tension here. It'll be easier to use in our next step. If we look at we have 6 equations, and we have 8 unknowns, though, 3 of which we were able to solve already. There's still 5 left. Since we have more unknowns than equations, we need more equations in order to solve them. These only come from the equilibrium. We have to add equations now based on, we have equilibrium equations. Now we want to consider the motion and how those equations are going to be added. We came up with 2 motion scenarios in this case. I will do A, I'm going to call block B slipping alone. Again, these are always analyzed on the verge of this thing happening. So when block B is on the verge of slipping, we're going to have a 7th equation. What equations become true under scenario A? Block B is about to slip. Friction force A is at its maximum value, which is going to be 0.3 times NA. And what else is true for scenario A to be on the verge of happening? Right, the surfaces that are going to slide with respect to each other, FRB and FRA, or this top surface and this top surface, are simultaneously at their maximum value. Both of these are true simultaneously when we're on the verge of slipping. This will be 0.4 times NB. NA we already know was 50. NB we already know was 75. In scenario A, we've added equation 7A, 8A for now between these 6 and these 2, 8 equations for 8 unknowns. Solving all 8 of these simultaneously, under scenario A, we get a value of P of 45 pounds. Like we saw with the crate one the other day, we have to consider all of the possibilities and then analyze which one of these is going to happen first. Because it takes 45 pounds to just be on the verge of slipping B out from in between A and C. The alternate was, there was only one alternate, is that block B and C slip. So we'll have a different equation 7, and a different equation 8, or possibly different 7 and possibly different 8. If B and C are going to slip, then what are the 2 equations that must be true when this is on the verge of happening? Right, the 2 surfaces, the 2 contacting surfaces this time change. It's now between A and B and C and the ground. Rather than in scenario A, it was between A and B and C. So actually 7B is exactly the same. It's still 0.3 times NA. Potentially it could have been different though. But 8B is different because it's FRC at its maximum value of 0.35 times NC. Again, we know NA is 50. We know NC is 90. So for scenario B, we combine the first 6 equations with 7B and 8B, and we get a different value of P. In this case, is 46.5 pounds. These were the only types of motion that we identified, so now we want to compare the possibilities. It takes 45 pounds for scenario A to be on the verge of happening, 46.5 pounds for B to be on the verge of happening. Which one of these is our answer for the minimum force required for motion to occur? The 45 pounds. This will happen first. Once we We're under the presumption we're not instantaneously applying the 46.5 pounds, that we're kind of ramping up to the 45. Once we hit 45 pounds of pulling, it's in motion, then these 6 equations stop being true. So we can't get to the 46.5 pounds. Therefore, once we hit the 45 pounds, we're in motion, and that's the most force we can apply before motion is going to start to occur, the 45.